I hope you're all doing great. I am Mr. H. Thank you for joining me. For this video, we are looking here at a cycloid, but a differential calculus application of this cycloid. In the previous video, the tag of which I'll include in the information section of this, I showed you how to derive these parametric equations which describe a point on the cycloid. X was equal to r times theta minus sine theta, y was equal to r times 1 minus cosine theta. A specific point on the cycloid of course has an x and a y coordinate value, and that gives you the parametric equations. Anyhow, our task here is to find a slope of a tangent and the equation of a tangent line to this cycloid if theta is equal to pi over 2. In the previous video I didn't make it very clear, but you're looking at 0 to 2 pi r to 4 pi r. I was omitting these radius signs, these radius variables, because I was looking at everything with regards to theta variable, but the correct designation is here as you see. If I'm looking at theta is equal to pi over 2, imagine pi over 2 is right here. Then we are looking at a tangent over here at this specific point of theta. We have to find the slope and the equation. The arch of the cycloid represents each of these. It looks like an arch, but that's the arch. How can you go about determining the equation and the slope of this tangent line at that specific point, theta equals pi over 2? You can. The best way to do it is to start with the slope determination. The slope of a tangent represents your instantaneous rate of change, which is derived from the derivative factor, the dy over dx. But since we have a theta parameter, we're looking here at dy over d theta divided by dx over d theta. Algebraically, if you manipulate this, a d theta variable goes and you end up with dy over dx. You're going to look at what will be the derivative of your y equation, which is r times 1 minus cosine theta. We would have to do the derivative first. Here I'm just making the framework. Divided by the derivative of the x equation, which is r into theta minus sine theta. When you do the derivative of this top, you know the r's can cancel out, but you're really looking at a sine theta. Here you're looking at a 1 minus cosine theta. If theta was equal to pi over 2, you plug that value here into your derivative factor to arrive at your instantaneous rate of change, that is the numerical derivative or the slope of your tangent line. You're having a sine of pi over 2, which is a 1, divided by 1 minus cosine pi over 2 is a 0, 1 over 1, which is equal to a 1. The slope of the tangent is equal to 1. Now we have to find the equation of the tangent. You know it's always y equals mx plus b. But how can you determine the y and the x, the actual value or the expression? Well, you have these equations. If you were to put the theta variable of pi over 2 in places of that, you can come out with the x and y values, which you can put into your equation. You know the equation y equals mx plus b. Then you can solve for this b and then actually come up with your linear function of that tangent line. X is equal to r times pi over 2 minus sine pi over 2, which is 1. You're really looking here at a pi over 2r minus r. That's your value of x. Y is equal to r times 1 minus cosine of pi over 2, which is a 0, and you're just getting here an r. You have an x value, you have a y value, you have a slope value, you have enough to determine that b. Y, which is equal to an r, is equal to everything else which will follow. Your slope, which is a 1, times your x value, which is pi r over 2 minus r, plus b. Solve for this b. B is equal to, you take everything on the other side, r plus r will become a 2r minus pi r over 2. I have now everything I need to determine the equation of the tangent line, which is y is equal to m, which you know is a 1. It's meaningless to write a 1, but you have an x plus b. B is all of this. 2r minus pi r over 2. If you want, you can separate this out, but this right here represents the equation of this tangent line at this point where theta is equal to pi over 2, and you know the slope of that tangent line was 1. But this is all I wanted to present to you with regards to the tangent of this cycloid, a differential calculus application. But thank you for watching this video. Have a good day.